Okay. So it's a pleasure to introduce our next speaker, Takao, from AIST in Japan, talking about practical location privacy attacks.
Okay. So thank you for introduction. I'm Takao Murakami with AIST Japan. And today I'd like to introduce expectation maximization tensor factorization for practical location privacy attacks. Okay. First, I will explain the outline of our work. We focus on Markov chain model-based location privacy attacks, which has been widely studied in the literature. In this approach, the attacker divides an area into some regions and partitions time at a fixed interval, such as 30 minutes and 1 hour. Then the attacker trains a transition matrix for each target user, and using these transition matrices, he can de-anonymize mobility traces or infer actual locations with high accuracy when the amount of training data is very large. But in reality, training data can be sparsely distributed over time. For example, many users disclose only a small number of locations via SNS, and they disclose not continuously but sporadically. For example, they may use only 1 or 2 check-ins per day, per week, or even per month. So in such cases, the number of training locations can be very small, and there are many missing locations in the training trace. And as a result, training transition metrics can be a very challenging task. So we consider a near worst case scenario for attackers, which may reflect the reality. In this simple example, there are no continuous locations in the training traces of user U2 and U3. And as a result of maximum likelihood estimation method, no elements are observed in matrices P2 and P3, which are corresponding to user U2 and U3. So in other words, we don't know anything about P2 and P3 in this case. And using these matrices, we can't de-anonymize traces of U2 and U3. So I'd like to ask, is it possible to de-anonymize traces using such training data? And we show that the answer is yes. We propose a training method that outperforms a random guess even when no elements are observed, like P2 and P3, in more than 70% of cases. This is an outline of our contributions. So next, I will explain the details of this work, and I will give a general introduction to location privacy and related work. Recently, many people are using location-based services such as map, route finding, and location check-in. And as a result, a great number of mobility traces called spatial big data are collected into the LBS provider. And this big data can be provided to a third party for analysis or made public to provide traffic information. While this data is very useful, there are some serious privacy issues. For example, a mobility trace can contain sensitive locations such as homes and hospitals. And even if a username is replaced by a pseudonym, the anonymized trace may be de-anonymized using the Markov chain model. So next, I will explain de-anonymization attacks using this model. Here, we consider we consider that the attacker is anyone who has anonymized traces. Okay? But we accept the LBS provider because the LBS provider has the original traces. So for example, if the LBS provider provides anonymized traces to a third party for analysis, then the third party can be an attacker. And this attacker obtains training locations that are made public, for example, via SNS. Then he trains transition matrices and de-anonymizes traces using the trained transition matrices. But in reality, there is a sporadic training data issue, which means that training data are sparsely distributed over time because many users disclose only a small number of locations sporadically. And this simple example, there are no continuous locations in the training traces of user U2 and U3 due to missing locations. And if we don't estimate missing locations, we can't train P2 and P3. So as a result, we can't de-anonymize traces of U2 and U3 using these matrices. So in this case, we need to somehow estimate missing locations in the training traces. And the previous work to estimate missing locations is based on the Gibbs sampling method. This method alternates between estimating Pn and estimating missing locations of Un until convergence independently of other users. But there is a challenge when there are few continuous locations in training traces. First, we can't accurately estimate the initial value of Pn because there are few continuous locations. And then we can't accurately estimate missing locations because Pn is not accurate. So unfortunately, this method may repeat these steps, and the final estimate of Pn is not accurate. So in this work, we address this challenge by estimating Pn with the help of other users instead of estimating Pn independently. This is our proposal, EMTF. So I begin by explaining its overview. Okay. The basic idea of our proposal is to use the help of similar users, that is, other users who have similar behavior. We first estimate unobserved elements, which are indicated by question marks, with the help of similar users. And for completely unobserved matrices, we substitute an average matrix over all users. And we can do all of them using tensor factorization, which was used in our previous work. And then we estimate missing locations. Here, blue location is an estimated location, and black location is a user-specific location disclosed by this user. And thanks to tensor factorization, we can estimate missing locations with the help of similar users. And then we go back to step 1. That is training transition matrices again. Here, very importantly, each matrix now captures a unique feature of each user's behavior because the estimated locations are accurate and a trace contains a user-specific locations. And then we continue step 1 and step 2 until convergence using the EM algorithm, which is an elegant method to train a model while estimating missing data. So next, I will explain tensor factorization and the EM algorithm. Tensor factorization is used for item recommendation, and it factorizes tensor into low-rank matrices. And in this work, we regard a set of transition matrices as a third-order tensor and use tensor factorization. Then we can estimate unobserved elements with the help of similar users in the same way as item recommendation. And we incorporate TF into the EM algorithm. The EM algorithm trains a parameter from observed data while estimating missing data. Oh, sorry. More specifically, it estimates missing data in the E step and trains the parameter in the M step and repeat these steps. And in this work, we estimate missing locations in this step, and we incorporate tensor factorization in the M step. And the feature of EM algorithm is that each EM cycle is guaranteed to increase the posterior probability of the parameter. So by incorporating TF into EM, we can find the most probable tensor and missing locations with the help of similar users. And this is the EMTF algorithm. In the E step, we estimate a distribution of missing location vector, QZ, by using the forward-backward algorithm. And in the M step, we estimate parameter by solving this optimization problem. And here we use the fact that the maximum of log posterior is equivalent to the minimum of regularized square errors. Then this problem is quadratic with regard to one parameter, and we can alternately solve this optimization problem. But unfortunately, the time complexity of both E step and M step is exponential in the number of missing locations. So next, I will explain this problem and how we addressed this problem in details. And the time complexity of EMTF is exponential because the number of possible missing locations is exponential in its length. For example, if the number of regions is 256 and the number of missing locations is 8, then the possible Z is 64 bits, and it takes too much time to compute its distribution, QZ. So we propose two approximation methods. One is based on the VW algorithm, which approximates QZ by the most probable value. And the other one is based on FFBS, which approximates QZ by random samples. So FFBS approximates QZ in a more accurate manner. And both methods can reduce time complexity from exponential to linear and make EMTF practical. OK, so we performed experiments to evaluate our proposal. But here, I explain only the most important part because I have no time. For example, we used 3 data sets in our work, but here I explain only 1 data set. So for more details, please see our paper. Here we explain the Goara data set, which contains mobility traces all over the world. And we used traces in New York and Philadelphia, which is divided into 16 by 16 regions. And we used 250 users and extracted training traces and testing traces separately. And we randomly deleted each training location with probability 80%, like this figure. And then no elements in the matrix were observed in more than 70% of cases. So in other words, this is an extremely sporadic training data scenario, which is a near worst case scenario for attackers. And we evaluated the de-anonymization accuracy. Specifically, we performed the Bayesian de-anonymization attack, which selects for each testing trace k candidates whose posterior probabilities are the highest. And here we have the result. This is the relationship between the de-anonymization accuracy and the number of candidates. And the black dot line is the performance of a random case. So we can see that ML and TF are almost the same as the random guess because they didn't estimate missing locations. And we can also see that GS was worse than a random guess. This is because it didn't accurately estimate missing locations. And on the other hand, our proposal, EMTF, outperformed a random guess, and EMTF using FFPS provided the best performance. So as a conclusion, we can say that EMTF is very effective in a sporadic training data scenario. Okay, so I'd like to finish with a summary. Our training method significantly outperformed a random guess, even when no elements were observed in more than 70% of cases. And as future work, we'd like to evaluate a state-of-the-art obfuscation methods, such as geo-indistinguishability, applied to sporadic training traces like this. Okay, so thank you for listening.
And we have a little time for questions. Rachel.